Perfect. Okay. Hi, everyone. I'm Alessio, and I'm going to talk about some work I've been doing with my advisor, Niki Vazou. And the subtitle of this talk is like, I would like to copy paste code from dependent types into my liquid Haskell file and have it compile. Okay, so quick refresher, what are refinement types? The idea is that we have like some sort of like base type system, and we add predicates so that we can refine what our types are able to express. So for example, we have like integers and we are able to just talk about indexes that are integers that are even. And in liquid Haskell, predicates are Haskell Boolean valued expressions. So I will stress that there are no quantifiers. And people will say, okay, everything is decidable is like very boring. But already with this, we can do like already like some nice stuff. We can do normal programming. We can define list and define the operation for like appending to a list. And we can prove that, for example, is associative. So it's like just like a proof like by induction. We have like the base case. And then like here, we just do the induction and the SMT solver is gonna deal with like using congruence to actually have the actual proof. Okay, but every Haskell program is a compiler. So if you want to prove stuff about our Haskell programs, we need to, I don't know, sort of like talk about meta theory of programming languages. And like the hello world is doing like some proof about the simply type lambda calculus. So yeah, we can appreciate for like a bit. This is like super complex rules. And our idea is that we want to encode these rules in liquid Haskell. And actually, we can sort of do it. And if you, for example, are familiar with Agda, it looks like very similar in the way that you would do that in Agda. So like you would do that through indexed types. You have your application. So you take like a term that has like type from sigma to tau, another term that has type sigma, and then you obtain a term that has type tau. But I never mentioned indexes when I explain like refined types. And the trick is that we straight up lies to the user. So we use like prop to sort of like give some sort of like syntax for indexed types. But what we are actually doing is we are sort of axiomatizing the behavior of like this function prop that is actually assigning indexes to values of type term. And in the case that this thing is like something that is decidable, technically you could define like prop as a Haskell function and define untyped term and then define the type term with like the decider. But these things actually works also with like undecidable properties. And I guess like one of the neat thing about the refinement types is that you can like hide all the non-computable stuff inside the refinement and it's not gonna taint your code. So like proof extraction is practically free. Okay, now we want to represent values of the lambda calculus. We want to talk about like theorems about it. And we want to do it with a shallow embedding. So we can represent our object language integer with our meta integers and with and our object arrows with actually function types in our meta language. And here we have like to pick one of the two possible ways. We can encode them through like a data type or with a function that is actually producing a type. So we can try with the first approach, and that is the way that you would do like independent types. So we do large elimination. So you're on your object types, and you produce your actual type in your meta language. But the thing that is happening is that, I mean, you're producing a function that goes from like values to types of your language. Yeah, so we are producing a type. But does it make sense to do something like that in refinement types? Not really, because you have like to write the actual function. Okay, the type of the argument is pretty clear, but what I'm supposed to put there? And the answer is like, yeah, no, we cannot do it, full stop, because like what the dependency that you have with refinement types is that, okay, you can mention tau here in the refinement part, but that type needs to be like an Haskell type. So, I mean, this thing is not gonna work. We need to go the other way. We are forced to use data types. So we can go through this like very naive encoding. So we have like a different constructor for each type of values, and we sort of wrap our meta representation of our value representation in the meta language with the constructors. But yeah, negative occurrences, everyone is scared, we leave the room. But yeah, and this is like an extract for like software foundation. So this is like something that you actually do when you are like learning dependent types. And yeah, like, okay, Coq is gonna reject this definition because it's violating the strict repositivity requirement, because you can use that to encode non-terminating functions. So it turns out that you can define this thing with a fixed point, which in if you give like good names to stuff in your dependent type programming language, you're gonna use a function to do that. But we already seen that we cannot do that. And now we're gonna see why negative occurrences are bad. So here we are declaring this data type, which is called bad, and it has like the same bad in negative position of the arrow. And the problem is that we are not guaranteed that there is initial algebra. And this is like very problematic to give like the semantic of the data type. You can just think about it like you are supposed to solve like this fixed point equation. So you want bad arrow void to be equal to bad. You can look at the sizes and you can just like not very constructive say, okay, if my bad type is empty, then I am going from an empty type to void. So I have one inhabitant, and that it means that my type is not actually empty because I have at least one inhabitant. So I can try with like a type that is not empty, but then this type is not empty. I don't have any function from like an empty type to void. So actually my type is empty. So there is no way to define the semantics of this thing. But what we see is that we are sort of expressing like this non-monotonic feature of like the arrow type when we have like a variable on the non-positive side. But what we know is that strict positivity is a condition that implies the existence of the initial algebra is not an if and only if. So there are no strictly positive types that actually have initial algebra. And I would argue that we have like a pretty unequal treatment between data types and functions, in the sense that we force well-definedness of like data types with the positivity checker, and we enforce well-definedness of function by determination checker. But it feels like the function termination argument is like spot on, is like what I actually want, but with data types feels a little bit unfair. It looks like if we translate what you are doing with data types right now, is like saying that a function is not terminating because it's recursive. But instead, when we check for termination of function, we look also at the arguments. So I'm gonna argue that actually this data type here is fine, and I'm gonna say that we are, yes, negative, but we are in a smaller way. So the first thing that we need to note is that we are not actually declaring a single data type, but a whole family of data type. And each actual data type is like the instantiation with the index. And I'm going to argue that if you fix like a partial order on the indexes and in negative position, you are like recursive. You are like referencing the same data type. If the index is smaller, then that thing is fine. And the argument is that we are using this sort of like partial order on the indexes as a proxy to say that if I define new values with this constructor, these values are not going to influence the type of values that we have here. So we sort of circumvent like the non-monotonicity that we have with the arrow type. Okay, in this case, we just use like the partial order that we have like structurally on our object types. And technically, this thing is not very dependent on refinement type system. It should work also on dependent types. And one application that I can, for example, think for dependent types is when you want to do higher order abstract syntax, that you sort of have like a negative occurrence. Okay, so our problem is that our refined type systems aren't expressive enough for some proof. And the solution is that, yeah, maybe we should allow some negative occurrences. Obviously, my argument was like very unwavy. It's not like a real proof. So like what we are working on right now is actually like to make the argument like more formal, I would say. So thank you for your attention. You can actually try it with Haskell online. Pretty much everything is implemented. Modulo like the smaller negativity checker, but you can just disable the positivity checker and check yourself.